Have you ever stopped to wonder what connects the adrenaline pumping through your veins, the dye that gives your favorite shirt its color, and even the numbing agent the dentist uses? Well, the answer is a totally fascinating and absolutely essential class of molecules. Today, we're diving deep into the world of amines.
And hey, don't just take my word for how important these are. The source material for this whole explainer puts it pretty bluntly. Their number one job in our world is to be the starting point, the raw material, for creating the stuff we depend on every single day, from life-saving medicines to high-tech fabrics.
And the list of where you find them is just mind-blowing. We're talking about crucial hormones like adrenaline, anesthetics like Novocaine, even something as common as Benadryl. But it goes so much deeper than that. They're literally part of the building blocks of the proteins and vitamins inside our own bodies. And in industry, they're the key to making dyes, plastics, even the surfactants in your soap. They are, and I mean this, everywhere.
Okay, so that brings us to the main event. We see what they do all around us, but what is an amine really, like at its most basic chemical level? To get that, we have to go back to the beginning. We've got to meet the parent of the entire family. Yup, it all starts right here with one of the most famous molecules in all of chemistry, ammonia. It's got this simple pyramid shape, just one nitrogen atom with 3 hydrogens hanging off it. This little molecule is the blueprint for every single amine that exists. So here's the official definition. An amine is what you get when you take that parent ammonia molecule and you start swapping out its hydrogen atoms for something a little more complex, these carbon-based chains or rings that we call alkyl or aryl groups. Honestly, the easiest way to wrap your head around this is to picture a family tree. Ammonia, NH3, is the original ancestor at the very top. Every other amine you'll ever come across is just a direct descendant, a slightly modified version of that original ammonia structure.
And, just like in any big family, you can group these descendants into different branches. The way we do it is by counting how many of those original hydrogens have been replaced. That gives us 3 main types of amines. So here's how that family tree branches out. You start with the parent, ammonia. Swap out just 1 hydrogen, and boom, you've got a primary amine. Swap out a second one, and now you're looking at a secondary amine. And if you go all the way and replace all 3 hydrogens, you've made a tertiary amine. It's that simple step-by-step process that creates this huge, diverse family of chemicals. All right, so now that we know the family structure, let's talk about their personality. Their chemical character, what makes an amine act the way it does. Well, one of their most important traits comes from the nitrogen and hydrogen atoms they've got. See, primary and secondary amines can form something called hydrogen bonds with each other. Think of it like a type of molecular stickiness that has a huge effect on their physical properties. And you can really see this stickiness in action when you compare these 3 compounds. They all have almost the exact same weight. But look at the boiling points. The alkane, with 0 hydrogen bonding, boils at a chilly 300 Kelvin. The amine, with its hydrogen bonds, needs a lot more energy. It boils way up at 350 Kelvin. Now, it's not quite as sticky as an alcohol, which boils even higher, but it's way, way stickier than a simple alkane. But as important as hydrogen bonding is, the real defining chemical trait of the entire amine family is that they're basic. Because of a lone pair of electrons just sitting on that nitrogen atom, amines are fantastic at accepting protons, which is the very definition of a base. So here's the crucial part. Those descendants, the alkylamines, are usually stronger bases than their parent, ammonia. Why? Well, those alkyl groups, the R groups we added, they have what's called a positive inductive effect. That's a fancy way of saying they actually push electron density toward the nitrogen atom. This makes that lone pair of electrons even more exposed and available to snatch up a proton, which in turn makes the whole molecule a stronger base. This leads to a really logical question, right? If adding 1 alkyl group makes it a stronger base, does adding 3 of them, like in a tertiary amine, make it the strongest base of all? And in a vacuum, yeah, it does. But in water, where pretty much all chemistry actually happens, the story gets a whole lot more interesting. See, in water, an amine's basicity is a really delicate balancing act between 3 different things. First, you've still got that inductive effect, with the alkyl groups pushing electrons. But then you also have solvation. That's how well water molecules can surround and stabilize the amine once it grabs a proton. And finally, you've got something called steric hindrance, which is just the simple fact that big, bulky alkyl groups can literally get in the way of the water molecules.
And this chart just shows the result of that balancing act perfectly. For these amines in water, the strongest base isn't the tertiary one with the most alkyl groups pushing electrons. It's the secondary amine. That's the one where you hit the sweet spot, the perfect combination of electron pushing, good stabilization from water, and not too much bulk getting in the way. It's the most effective base of the three.
Okay, so let's bring this all back around. We've seen their family structure, we've talked about their chemical personality. Why does any of this matter in the real world? Well, it all comes down to this. Their specific structure and their adjustable basicity are exactly what make them perfect chemical building blocks, or what chemists call intermediates. That reactive lone pair of electrons on the nitrogen is like a perfect handle that allows scientists to build much larger and more complicated molecules. This reactive character is the whole secret. It allows amines to go through reactions like acylation, which creates amides, structures that are vital in countless pharmaceuticals. It also lets certain amines form diazonium salts, which are the gateway to creating a massive variety of colorful dyes and all sorts of other useful compounds. This is the chemistry that directly powers our modern world. So when you really stop and think about it, it's pretty incredible. From one tiny, simple pyramid-shaped molecule, ammonia, this entire family of descendants has sprung up. A family so important that it helps run the chemical reactions inside our own bodies and forms the backbone of massive global industries. It really makes you wonder what other simple shapes are out there quietly building the world all around us.